like a day off, so I asked.
Yeah, I haven't taken a day off. Otherwise, I have to go and get my hair done.
Yeah, but you're okay.
Yeah.
So really, well, and
It's
Okay,
streaming live now.
We're live on YouTube.
Christoph, I promised to send you something. Do you want? Shall I send you now?
I'm gonna start screen sharing from my
Oh,
side.
don't worry, I have enough about you.
Okay, I'm gonna mute everyone now, okay? Okay, the three of you are there.
I'm here.
Hello.
Maybe we don't need Jonathan now, but I will introduce you, Jonathan, in my talk, and then in the Q&A we'll have you. Okay?
Sure. So I'll close the video.
Yeah, sure.
Okay, great.
Okay, Doron, you and Christoph. Christoph, would you like to kickstart or Doron?
Are we broadcasting now?
Yes, we are live on YouTube and we're broadcasting.
Okay, so good afternoon for all the millions watching us now, or I would say afternoon, morning, or whatever time it is for you. Christoph, do you want to say a few words, and then I will introduce you in my talk.
Sure, it's a pleasure to introduce a good friend, Doron Friedman, who is at the moment a professor, unbelievable, but he's a professor at IDC in Herzliya in Israel in the Advanced Reality Lab. It's a very nice spot if you want to go on holidays. I recommend Hotel Daniel. And he also did his computer science studies at Tel Aviv University, so the major university in Israel. And then he did a postdoc at UCL in London together with Mel Slater in the famous virtual reality and computer graphics lab with Anthony Steed and so on. And he was also involved in many different startups in different countries. And he works mostly on telepresence, virtual reality, human-computer interfaces, brain-computer interfaces, and we worked together for many years in several European Union projects like Presentia and Vere. And Doron was always responsible for combining BCI technology with virtual reality, and I'm looking forward to his talk.
Thanks a lot, Christoph. So I guess I'll try to share my screen. Okay. Right. So I will, it's a bit difficult to be talking to myself without any feedback, but I guess that's what the world has become right now. Hopefully we will be over this soon, but today we're here to talk about research. And so this, in my lab in IDC Herzliya, it's actually the first and only private university in Israel. And we look at, we're interested in this human-machine confluence, this synergy between humans and machines. And we look at virtual reality as maybe the ultimate display, and brain-computer interfaces may be the ultimate interface. So we look at them both separately and together. And the agenda for today is as follows. I will assume everybody's familiar with VR, especially with all the talks that hopefully you've heard right now from this series. So I'll give a very quick high-level overview of BCI. Then I'll talk about some classic BCI VR studies that I was fortunate to take part in. And then hopefully we'll have time to discuss what we're more interested in the last few years, which is going beyond explicit control. Hopefully we'll have time to discuss this. And then I do hope to have people around and take advantage of the live opportunities on both Zoom and YouTube. So you can ask questions during the talk, and then we can all have a discussion and try to address them with Christoph. Of course, he's a BCI expert and the head of gTec, who's been very important to this field. And with Dr. Jonathan Giron, my colleague from here from IDC Herzliya. I will also mention one of the projects, one of Jonathan's projects somewhere in my talk. So hopefully we can maybe even argue during this discussion. So very quickly, you know, this is what we would like to have. This is kind of the holy grail, a non-intrusive device. And, you know, maybe like the Muse that you see here. And maybe you don't even need to type with your thumbs or anything. It just reads your thoughts and you can communicate with any device, or maybe the phone reads your thoughts. As you all know, we are very far from this vision. The reality is more challenging because, to get good signals from the brain, and, EEG is the most accessible signal. We'll talk about others as well, but getting good signals is still requires devices that are obtrusive, the signals are noisy, and the brain is very complicated. So we're talking about, 10 to the power of 11 neurons, roughly 10 to the power of 15 synapses. And so, it's roughly, arguably you can say it's about as complicated as the internet is, or maybe even more complicated. And we're trying to figure out, imagine you're trying to figure out what goes on the internet with a few electrodes from far away, outside the scope. So it's really wonderful that we actually can do something. And, and if that's not enough, then the mind is obviously complicated. And this relationship between the brain and the mind, we want to read the quote unquote thoughts, and the relationship between the signals and the mental patterns are not, it's still a mystery. So we do have a lot of challenges. So I think if you're a young student, I think it's definitely a great field to get into, because it's definitely going to be one of these things that's going to transform humanity. But you do have many years of challenges in front of you. So very quickly, so with humans, at least, we're very limited with the type of signals that we can extract. I think that's the main problem we're facing today with BCI. With animals, they can do all kinds of things, which I'm not going to talk about today, allowing for very good control. But with humans, we're more or less limited to these signals, at least non-invasively. And each signal has its own advantages, but mostly disadvantages. So, for example, fMRI, I will talk about it, can give you relatively good information, but of course it's not only expensive, it's also not very accessible for something what we actually want to use interactively. Similarly, these devices, EEG and also FNIRS, in theory, they could become low cost and friendly and relatively non-intrusive. In theory, they're not there yet. But because they are measured, the signals are measured from outside the scalp, we have a big problem of low spatial resolution. These methods, which are not based on direct electrical activity, but on surrogate activity, which is the blood oxygenation level, so you have the problem of temporal resolution. So as you can see, we have quite challenges with the signals we're trying to use. And we do have invasive studies with humans. In fact, I think that's where most of the exciting breakthroughs are happening in BCI. Sometimes when it goes invasive, they change the name to BMI, brain-machine interface, but it's the same idea. And I'm not going to talk too much, I'm not going to talk at all actually about invasive BCI. Definitely there's a lot going on there, but today it's about integrating with virtual reality and not about these very rare and very extreme medical experiments and interventions. So that would have to be another talk and less related to HCI and virtual reality. I want to introduce some taxonomy, which is especially, I think we should broaden a little bit the scope of BCI. So what I call classic BCI is where we use the BCI for explicit control, right? When you try to control a device, mostly disabled patients trying to control a wheelchair or to communicate, maybe also gamers or someone trying to navigate in a virtual reality, but this is what we call classic BCI, and when the BCI is used for explicit control. And then we have extensions of the field. Then there's passive BCI. I don't think anyone likes this name except Thorsten Zander, our colleague from Berlin, who came up with it. The idea is that you, the user, are passive, and so you are basically doing a task with an application, and the application is responding to your either cognitive state or emotional state, and that's what we mean by passive BCI. You should have better names for these kinds of things. And then there's, of course, neurofeedback, which we're going to talk about briefly. And there's the classic protocols from, I think, the 1970s, where you try to up or down regulate alpha, and stuff like that, but you can also do some use some techniques which are much more complicated. So of course, the lines between them blurred, but as you see, the goal is very different. The goal is for you to be able to regulate specific circuits or some activity in your brain, and then hopefully have a long-term impact on your brain activity. So we'll start with a classic BCI, and together with VR. So as you can see, we're still more or less stuck with 3 classic paradigms for controlling BCI by thought. And you see that all of them are from the previous century, especially if someone can help me find the older reference for SSVP control. Of course, it's a well-known effect, but if someone knows of earlier BCI work with SSVP, that would strengthen the point. But anyway, you see we are still working with 3 paradigms from the previous century. Motor imagery. Fortunately, we have this homunculus relatively close to the cortex, so we can distinguish using EEG, right hand, left hand, feet, maybe even tongue, stuff like that. And then there's these 2 methods, SSVP and P300, which you can think about them a little bit as tricks. Although they're interesting, of course, each one of them is interesting, but you can see that, you have these arrows. Each arrow is flickering in a different frequency, and you can use them, for example, to move. This could be an augmented reality application. And on the right, you see a P300 spelling, a classic spelling application. The rows and the columns are flickering very quickly. You are attending to a specific letter. When your letter flickers, either because of the row or because of the column, you get this nice P300 evoked related potential. So these 2 can be SSVP, the steady state visually evoked potential, which is deciphered from, I forgot to say, the frequency that flickers is then very nicely reflected in your occipital areas in the brain, and it can be decoded from there. So it is pure control of an application with the brain, but it's using these exogenous responses. You cannot just think about something and it happens, which is more or less what we get with motor imagery. You can imagine your hand moving. For example, you can imagine playing tennis and you see your avatar or your actually playing tennis. So this is why when we started working on these European projects, we were mostly interested in motor imagination, and we realized that navigating in the virtual reality is a very good application. And so we looked first of all at motor imagery, and we were fortunate to collaborate with Gerd Förtscheler from Graz, Austria, who is one of the pioneers of BCI in general and the motor imagery paradigm. So the idea is that you look at these spatio-temporal patterns, both in the frequency domain and certain areas on the cortex, and with a lot of effort in training the subject, signal processing, machine learning, you can basically distinguish, as I said, left hand, right hand, feet, etc. And I was fortunate to work on these projects as a postdoc, working in Mel Slater's lab. I hope all of you know Mel Slater by now, who organized this whole online seminars. So I think it was probably Mel's crazy idea around 2002 or 2001 that we should integrate BCI with immersive virtual reality. And I was very happy to be involved with that, together also with Robert Leb, the lead student in Graz, who was working on it. And of course, Christoph Guger and gTec were part of this project. A lot of the early work on BCI VR happened in this European project. So we had all these kind of projects. I'll quickly show you this video. I won't show the whole video.
Could a computer ever read a human mind? By implanting electrodes into the brain, could it access our thoughts, hopes, and dreams? This may sound like a futuristic fantasy, but it's exactly what some scientists are trying to do. Using video game technology, they have developed a new way of moving through virtual reality by thought alone. Thomas Schreier is paralyzed. He broke his neck in a freak holiday accident.
I ran to the sea and jumped over the waves, and one of these waves pushed my feet up, and I crashed with my head on the bottom of the sea.
Since the accident, Thomas has been unable to move his arms or legs. But thanks to a new European research project, he is learning to maneuver his way down a street, albeit a virtual street. The cap he is wearing is packed with sensors, which pick up electrical signals from the motor section of his brain and send them to a computer. When Thomas thinks about moving, the computer software translates a thought into a command. The harder he thinks, the stronger the signal becomes. When it's strong enough for the line to cross the red mark, Thomas moves down the street.
Okay, anyway, I wanna
Could a
go
computer
to the next topic. So this is kind of classic early work with it's quite amazing that a tetraplegic patient can actually move in the virtual environment by thought, work from almost 15 years ago. But note this is one button, so it's like an on-off toggle. Next, at that time already in Presentia, in the Presentia European project, we realized that navigation in virtual reality is cool, but we thought it makes sense to have a virtual body. Now let me explain. So the idea is that if you think about it, BCI is by definition a disembodied technology. It's bypassing your body. You interact, directly from the brain to the world. And, so it could be very interesting, from a philosophical or scientific point of view to study disembodiment. But, let me put it simply. We don't think disembodiment is a very good idea. Rather, we suggest re-embodiment. Okay, so early then in Presentia, we already did these first studies where you control an avatar by thought. You imagine your hand, the avatar waves. You imagine your feet, the avatar starts walking. This was very difficult. So it's 3 subjects, small conference paper, and then a journal paper later on. But the idea is that, and by the way, if you see, we're using the cave. These are the days before, of course, we had HMDs, but they were very heavy, very bulky. So it's a third-person perspective, okay? But the idea is that today with an HMD, of course, it would be much more natural. And indeed, this is a slide from today, actually a video. Let's see this video that I got from, I asked Christoph to share the state of the art. So this is kind of 10, 15 laters. And here is where I want to be a bit controversial. Again, we can argue and discuss about it in the Q&A, but I think this is maybe the first and only BCI product, something that is actually used by people, not as a scientific experiment. Sorry for this. Yeah, so what you see here is patients, stroke patients, for example, who have limited control of their limbs. And let's say that ideally should be wearing an HMD. So you get this very nice closed loop where your brain believes that you are controlling your limbs perfectly using the virtual reality, even though you're not. And so it's not unlikely, and there is good evidence, growing evidence from several groups around the world, that this could contribute to the rehabilitation process. The brain sees that it can move the limbs, believes it, and finds a way to do it, and maybe to short circuit some brain activity, etc. Again, very promising, and maybe one of the few success stories we have so far with BCI, and I'm happy that it's related to this work that started many years ago in these European projects. So then, if you, between the lines, you can see that I was very frustrated with EEG as an input signal because, you know, of course, the fact that you can allow patients to try to use it is incredible, but the, you know, the noise, the signal to noise ratio and the bit rate you can extract is very challenging. So when we had another European project, we thought outside the box. And here again, I was fortunate to work with Rafi Malach, who's an amazing neuroscientist in the Weizmann Institute with basically an fMRI in his backyard. And most of what I'm going to show next is work by Ori Cohen that was part of it. That was his PhD, so a very good student working for several years. And we said, why not do BCI with fMRI? And of course, the usual response is that people thought we were completely crazy. You know, the first claim is that it's too expensive. Well, you know, with the whole field going invasive, I think, you know, surgery, either ECOG or, you know, or chronic implants are definitely not going to be cheap. So definitely it's worthwhile to use fMRI to ask questions about BCI. The next claim was that it's too slow. Well, I hope I will show you that with Ori's excellent engineering, we were able to do things that probably would be impossible with EEG. And maybe, unfortunately, we haven't done that, but we haven't done a head-to-head competition, but we may even beat an EEG BCI because we have more information in the fMRI. And then, of course, one of the best things about fMRI is that we have a coverage of the whole brain simultaneously. So yeah, actually it's fine. Imagine that even with invasive BCI, you only cover very specific areas. And with fMRI, you can see what's going on basically throughout
right hand or his feet.
So now I'm going to quickly show you some parts of this video of one of the special operations that we did. This is the first stage. This is the training stage where you control an avatar. So this is training both for the subject who's lying in the fMRI and seeing this. Of course, this is not immersive virtual reality. It's a non-immersive virtual environment displayed in the scanner. And so this, in the training stage, the subject trains to control the avatar, and the machine learning trains to figure out, you know, these, in this case, 3 classes, left, right, and forward, 2 hands and feet. Now, in the second stage of this experiment, what you see is the subject in Israel lying down in the fMRI scanner and controlling a robotic body, which is in France, this humanoid robot from the group of Abdel Khedar in Montpellier. And so you imagine that, in a sense, your brain is in Israel, your body is in France, and you see through the eyes of the robot. This is what the participant, the subject, sees. And you have to perform all kinds of tasks. In this case, first task is to follow a shape of an 8 to make sure the subject can turn. And then at some point, we hit this red teapot somewhere in the room. So again, you have to control a robotic body by thought using telepresence, and then look for this red teapot in a different continent. And this is what we think of as a BCI re-embodiment. Okay. So how does this work? So fMRI gives us relatively superior temporal resolution. What you see here is, you know, still averaged over, I would say, probably 40 trials. So, you know, on 40 trials, you get a very nice signal to noise. If you're looking for a single event, which is what we did, of course, with BCI, it's much more noisy. It's a challenge. But with Ori's system, we were able to reach very good accuracy, very close to 100% in most tasks. So Ori actually built this whole system, which I think is somewhere on GitHub, if people are still getting into this field, and maybe some parts can be resurrected. So what you see is in the training stage, there's a lot of pre-processing, filtering, And then there's a simple feature extraction, feature reduction. We use information gain to find the voxels with the interesting information about distinguishing between classes. And then this is sent to an SVM classifier. And then in real time, you can use the same models trained offline and integrate this with, it's fully integrated with Unity, but can also be used to control robots, as you've seen. So why is this interesting? So first of all, from BCI point of view, let me show you this video towards the end of the project. So what you see here is, first of all, you see a bigger robot, again, from Abdelkader's group in France. And what you see here is something that I think is very rare in the BCI world. It's a 7-class BCI. And again, this is not seven arbitrary SSVP frequencies, which has been done, of course, but this is 7 meaningful mappings between mental patterns to operations. So there's 4 classes for navigation, left, right, forward, and stop. You see this guy, the experimenter, doesn't trust us, so he moves the chair, but it kind of works. So what you see here is the subject controlling the robot, and there's very good control. And on the right, you see how things look like from the point of view of the subject lying down in the fMRI. And now here, so these were 4 classes, but after the navigation, you get an instruction about which object to select from this table. Okay, so you see, in this case, you're instructed to choose the face. Okay, this is because we want to know that you did correctly, so we tell you what to choose. And you can see that all 3 objects are on the table and in the frame. So it's not based on eye tracking or anything, it's based on actually extracting from the brain the object that you are mostly focused on, okay? And eventually the robot points to it and, with some more work, of course, can grab it and start doing things with this object. So, and the interesting things again is that, so these 3 categories of objects, houses, tools, and faces are of course recognized from high-level visual areas, which are well known in fMRI, but we did not have to configure the system to do it. It's just in the it's purely data-driven. The system finds the voxels that are most informative, and indeed it goes to the motor areas to find the motor commands, and to the high-level visual areas to find these object category commands. Next, there was this study with amputees. And in this case, we told the subjects, so there were 3 amputee subjects, 4 controls, and we told the subjects, look, you are allowed to use your fingers, again, mostly left, right, forward, to navigate this not trivial track inside the forest. And so use your move your fingers and your toes to move forward and left and right. But of course, the amputee subjects did not have one of their hand. One of the hand is missing. And what you can see is with fMRI, you can start asking very interesting questions. So first of all, they are able to do it. I will show you some results, but then you can ask questions about what happens to these brain areas after such a trauma, such as amputation. All of them were more than 1 year after amputation. The question, can you still use a BCI? And if you look at these flattened brain images on the left, so you see the bottom is a control subject. You see that the left and right are quite symmetric. And again, we're not going to get into neuroscience, but even if you're not a neuroscientist, you're not used to look at these fMRI figures, you can see that for the amputees, the patterns are not symmetric, and they're not similar to the patterns of an able-bodied person, but nevertheless, there is enough information for both hands, even the missing hand, and certainly enough for close to 100% classification. Eventually, the classification rate was close to 100%, both for controls and amputees, and you can see the trajectories that they were able to perform, including speed, not only reach quite far down the trajectory, but also slowing down before corners, speeding up in straight lines. So again, the advantages of fMRI is that it allows us to ask all these questions that we cannot, what are much more easy, much more difficult to ask with signals such as EEG. One more example, and this is not at all related to virtual reality, but I do want to mention this study. So this is what you see is, this is work by Tal Harmelech, again with Rafi Malach. This was a collaboration with Rafi Malach's group. And again, without getting deep into brain science, I want to give you the highlights of what's going on here. So in this case, this is a neurofeedback. You just tell subjects to control certain regions of interest in the brain, but using fMRI, you can choose very specific regions. And what you see here on the y-axis, you see how good people are at controlling this brain area. And you can see 6 brain areas, and you can see a very nice pattern. First of all, of course, there's a huge difference. Some areas are easy for people to control, and some areas are impossible for subjects to control, at least using our neurofeedback paradigm with auditory feedback. And moreover, this, how good you are at manipulating a specific or regulating a specific brain area is correlated with its place in the hierarchy. So places like early visual areas, V1, V2, regions in the brain, these were almost impossible to control, whereas high-level brain areas were much easier to control. So you see the first 5 areas are basically moving up the visual pathway, and the IPL is part of the default mode system. Again, not getting into too many details, what is considered a high-level brain area. So these are the kind of things we can start thinking about in BCI, like what is easy and what is difficult. Some mental patterns are obviously easier for people to regulate. And fMRI neurofeedback allows us to ask these questions. Right, so until now, I was discussing controlling, navigation, controlling avatars, and a little bit around it. Re-embodiment. Of course, you can study, and we did study disembodiment, or I would say supernatural scenarios. It's terrible loud. Wait 1 minute. Okay, so in this case, this is, I guess you'd call it telekinesis. So again, these are the days before Oculus. So it's a power wall, shutter glasses, and stereo projection, and you're in the star field, and you can control some of these stars using SSVP. So if you look here on the right, you see a classic SSVP experiment from our colleagues in Italy in the same European project. But you see, we find these squares or arrows quite annoying, and therefore something that we haven't seen enough is basically we have this Unity code that allows you to turn any Unity object into an SSVP target and basically control it directly with SSVP. This is Jonathan's work. I mentioned Jonathan will be joining us for the Q&A, and I think I'll have more to say about this study. Okay, quickly moving on. Right, by the way, this was also a collaboration with an artist called Miri Segal, and another collaboration with an artist called Daniel Landau. This is, I don't even know the Latin word. This is not telekinesis, this is actually controlling other people's bodies. So you see this subject who's actually paralyzed in a wheelchair is using motor imagery of hands and feet to control these vibrating devices on the bodies of the dancers, kind of trying to control their bodies. So again, for us, all these projects working with artists are really good when we try to understand interaction paradigms, the limits of BCI. Of course, later on, you have to follow them with rigorous experiments and with maybe better engineering. But I think there's a lot more to do in these spaces. And then, okay, let me show you.
At the Advanced Virtuality Lab in Herzliya, Israel, researchers are pioneering technology that will enable us to control computers and even a virtual body using only the mind, a power some might call godlike. The lab actually uses a brain control.
Not sure what's going on here, but
Concentrate on that red block. I mean, really think about it.
Okay, here's the point. So you play this game, and you know it's a really fun video game. So in fact, what's not very well shown in this video is you control this puck with your hands, you know, using a keyboard. You move it left and right to make sure that the ball doesn't drop. But, sorry. But,
try using your brain to break the blocks.
Kind of blocks that you can only explode using SSVP. So this is what we call a hybrid interface. And it's really fun and it really works. And I think we should see a little more of that because, you know, SSVP is so robust that you can actually do it. You can perform a task and use the brain as another, like as a third arm, if you will, or as a third control channel at the same time. Okay, quickly, let's go. Okay, so these were comments about explicit control of virtual reality, kind of classic BCI. Of course, there's many more studies done by other fantastic researchers in the field, which I didn't review. But next, I want to go into the more kind of exploratory domains. And for example, you remember this study where I showed you with the star field. So Jonathan did something very clever in his master's project. He realized that this effect works even if you're not trying to. You know, SSVP is a very robust effect. You're attending to some flicker and we get a resonance in your occipital electrodes. And so what he did is he basically put people and we told them, look, and you know, we're talking, well, even now, a lot of people, most of the students haven't heard about the possibility of BCI. So we say, look, you're gonna be in this movie or experience, and we're going to measure your brain activity. And please try to guess, why are some of these stars moving towards you and exploding? Some of them do and some of them don't. Try to guess why. And without telling you, you are, of course, controlling them with an SSVP. So this can be considered a quote-unquote unconscious BCI. And then Jonathan did something even more clever, and he found out that afterwards, so he had two conditions. One group who did this unconscious BCI and another group who got sham, they didn't control anything. And then he showed that the guys who were actually training unconsciously to control a BCI were better at performing a task with the SSVP. So of course this study needs to be repeated, I guess, because it's a very dramatic finding. Again, unfortunately, a relatively small study published in a conference paper, but I think, again, opens up many possibilities. And in fact, we did go and look at it more rigorously using the neurofeedback and the fMRI and the collaboration with Rafi's group and Michal Ramot. And again, one study that I'm going to talk about that has no VR in it altogether, but still I think is worth mentioning. So Michal Ramot was an outstanding postdoc at the time, now a PI. And what she did, I will explain again informally and from the point of view of the subject. Okay, so you're a subject, you go to take part in Michal's experiment, and you go to the scanner and you lie down there actually 5 days in a row, quite boring, and you hear two types of sound. One sound is pleasant, it's kind of a winning sound, maybe like a slot machine, and then you're told that you get more money, one more shekel, it's kind of like, I guess, 30 cents. And then there's an annoying sound, and whenever you hear it, you lose money. And we make sure you're awake and everything, but it's quite boring. You have no idea, why you're hearing these sounds. And in the end of each day, you're told how much money you received. And then by the end of the experiment, we ask the subjects, why do you think sometimes you got more money, sometimes you got less? What do you think happened? And they said, well, you know, we thought it was arbitrary. And we say, no, actually you could control it. Do you know how you controlled it with your brain? And of course the answer is no. And well, to make a long story short, what happened behind the scenes is that the subjects, the reward electrodes were connected to two regions of interest. Again, well-known areas in the visual area, houses versus faces, one of them to get more money. So basically look at the difference. And if you upregulate one relative to the other, you get more money. Other case, you get less money. And Michal showed very nicely that, first of all, most of the subjects, not all of them, most of them were able to regulate correctly and make more money than you would consider in chance level, even without knowing. So again, unconsciously controlling high-level visual areas. And moreover, and again, you can read the whole paper for more details if you're interested, there were some interesting findings in the pre and post resting state analysis of the brain. So again, an example of using fMRI, we can aim for very, very specific interventions in people's brains, kind of expanding the field of BCI. Now, the other thing I want to say, we did write about it briefly in this BCI for Real workshop that we had. And, you know, so of course you can use brain-computer interface for science, but for many people, BCI is first and foremost an applied field. You want to help patients, or you know, or allow people to control devices, etc. And so the way to put my suggestion is as follows. You know, the field, as you saw, is not very new. It's been around something like 30 years. Okay, so we've been doing BCI for 20 or 30 years. Now, in the early days, it's fine to show that you can do something with BCI. It's quite incredible and it's worthwhile doing. But I think today, if you want to move the field forward, especially if you want to do things that are applied, I encourage people to show me and convince me and themselves and everyone, of course, not only that you can do something with a brain, but that you can't do it in any other way, especially that using EEG. You know? So EEG, of course, it's not very comfortable. If you look around, I would bet no one is wearing EEG. It could be, you know, if there's a killer application, maybe people would wear EEG-based BCIs, but we don't see it coming. And so I think, yeah, the point is, prove to me that it's better to use the brain. And you can't get the same results without using the brain, because most other signals are easier to extract. And this is why I think I will wrap up in something like 5 minutes, I hope, but I do want to make a few more points. So in the last few years, what we built in the lab is this diagram. By the way, I'm really proud of this diagram, so tell me afterwards if you think it's terrible. What we see here is that we record everything that happens in virtual reality, and everything is synchronized, of course, a lot of time series. And then we record, of course, not only all the events in virtual reality, but also time series. So we record a scale or a subjective report. So for example, we want to study fear or stress or emotional state. Then we sometimes during the experiment let people use the controller to indicate their level of stress, for example. Or if not, then we can do it post hoc. But so we get a time series of subjective reports, which can be used for labels, as labels. And then we extract autonomous nervous activity, ECG, skin conductance, respiration, head motions, audio, which I'm not going to talk about at all today, but of course could include lots of useful information. Each signal is processed separately, and then together you extract a lot of features and you can feed it into a machine learning, either trying to see what happens in specific events or trying to predict subjective reports. Let me quickly show you an example of a study that we're actually wrapping up right now. So we have a job interview, and in a virtual reality, an immersive virtual reality. And again, this is actually, so I don't have the logo, this is funded by Joy Ventures in Israel. And the idea is to develop futuristic technologies for combating stress or in general neuro wellness. So we thought what could be stressful for the students, which are our subjects, and one of the things is job interviews. And so we put you in a kind of realistic job interview, but notice, so we're not using very extreme stimuli. So it's only nuances of stress. And then the whole scenario is interactive. There's, I guess, one of the things we're interested is in having continuous monitoring of your level of stress with relatively good temporal dynamics. And this is why we cannot more or less use heart rate variability. So heart rate variability is well known to correlate with stress, but it's a very slow pattern to trace. So, usually traced over several minutes. You could look at 20 or 30 seconds windows, but we wanted a better resolution. And then, of course, there's a problem of a ground truth. It's a big problem in these so-called passive BCIs or affective computing challenges, because people are not very good reporting their subjective emotions, feelings, state. In this case, we still try to predict reported stress. And so there were 28 participants. I'm going to show you very quickly some results. 28 participants, 18 questions, and only a third of them were supposed to induce stress. So we wanted to see the stress fluctuate during this 7-minute, roughly 7-minute experience. So these are the results quickly. So what you see first is that this is subjective reported stress, average, and in blue you can see the variance. So yes, there's a large variance between the subjects, but you can definitely see, and by the way, some of this is statistically significant. There's a statistically significant difference between several questions that were clearly higher, induced higher stress, as opposed to other questions that did not. So that's the first thing, which is good that we can manipulate stress. The second thing is that we try to see which of these features that we extracted from the physiological signals was most correlated with reported stress. And as you can see, we looked at respiration, skin conductance, phasic, tonic components, respiration, all kinds of features extracted from heart rate. Again, to make a long story short, there were only 2 features that were significantly correlated with reported stress. The minimum heart rate and heart rate deceleration, which I'll show you in a minute. They are, of course, very much intercorrelated between them. They're measuring more or less the same thing. And so we use a heart rate deceleration, which is more or less what you see here. Here's an example from a stressful question, stress-inducing question. You see this very nice deceleration, missing a heartbeat. And here's a question that did not induce stress. So this feature was found most informative, 0.6 correlation, which is quite good for such a psychological construct, but this is averaged over 28 participants. Now the question, can you turn this into a BCI-like interface? Can you detect stress momentarily? And if you look at this most informative feature, over time, over all events, 18 questions, 28 subjects, on a single trial basis, the correlation is still statistically significant, but you see that it is very low. 0.12 is only slightly better than chance, so we cannot use it for ongoing stress management in a BCI-like fashion. So you could say, okay, why don't you take all these features, throw them together into a machine learning classifier? Well, you could try. I suspect you wouldn't get much progress because we actually tested this with a regression. And here's a kind of regularization that you can do. It's called lasso regularization. Basically, what you're trying to do is make sure that these betas are as small as possible. And in fact, they all become 0 if their variables are redundant. And indeed, the results, as you can see here, is that the lambda, the regularization was very, very high. meaning basically what happened in this data, for the data we get, all betas become 0 except the beta for this heart rate deceleration feature. So it's kind of telling us that in this case at least, and under assumptions of linearity, only this feature is informative and we will not gain anything by adding more features. Of course, I think moving forward, I would add maybe EMG, which of course could contain a lot of information. So I'm not saying it's impossible, but I'm saying it's quite a channel. And I'm not sure EEG will help in this case. But this is a long story that we will not get into. What I do want to show you as a last, well, you know what, maybe I'll take 3 more minutes. Anyway, I'm talking to myself, you know, I can't see anything. I don't know if there's any people here on Zoom or YouTube, or if I'm talking to myself. Maybe Jonathan is awake, maybe not. But anyway, so I'll take 2 more minutes. And one of the things we're trying to do is automatically scare people based on their physiological responses. Work led by Karen, a student in the lab, and a very impressive study, which is almost completed just before the corona. I'll show you a sneak preview. This is really informal video captured naturally during the pilot. So, you know, this is, you try to scare people using all kinds of stimuli, see spiders, and they have to report, using this scale, they report their subjective fear. You know, claustrophobia, spider, snake, fear of height, etc., etc. And then, yeah, again, a sneak preview.
That's really a lot.
Oh, sorry. I insist on trying to watch that.
That's really a lot.
So this is not fake. This is a real pilot study with a participant, of course, agreed to share this video.
No, they're not coming to me. Jesus. How? Okay. Whew. That was a good one. Intense.
And you see
really
that,
intense.
then she, of course, turns this to the top. So the question is, can you automatically scare people using machine learning and physiology? And the answer is yes. Hopefully, we'll be able to complete the study after the corona. So, some early results are published. Of course, if we can scare them, hopefully we can also, you know, develop all kinds of relaxation protocols. Of course, our intention is not necessarily to scare people, but to make them feel better. And I do want to make this comment before concluding. So I think, again, as I said, BCI is an amazing field to be in. I think it's definitely one of these things that at some point will revolutionize everything, but sometimes we have the feeling that it's going very slowly. So one of the things that we try to do is have a larger audience. And so you see, back in 2013, we had the first brain hackathon organized by Hamutal Meridor, amazing. And you see in this hackathon, we had, you know, the head of Google Israel or Google R&D or whatever. We had Muse, Ariel. We had Steve we had Starlab people, we had gTec people, and we had hackers and we had scientists, and we put them all together. And I think these activities are very important to start getting outside of the box. And finally, and this might be a question to you, but I think Silicon Valley is, on the left you can see Silicon Valley hackers. We talked about the hackers, but you know that at least we have this guy called Elon Musk, who's not only trying to send space shuttles, but also working on a very ambitious BMI project. And some rumors, I haven't been following what's going on in Facebook, but my understanding is that these guys are putting serious efforts into making progress. And I think it's interesting. And I think it's interesting to note that both of them are actually doing the same thing that I was advocating much earlier, which is try to work out new signals, right? They're not using EEG, they're not using fMRI. They're trying to create new signals, better signals for future BCIs. So that's where I think we need to go. You know what? I'm going to skip the conclusion slide because it says more or less the same thing. You can take a quick look. And I do hope that I'm not, that there are some people around me still in the virtual space and we can have a nice chat. Okay, so now, how do we, I'm not sure if Sylvia is
I am here.
alive. Okay, great. So at least Sylvia, Christoph and Jonathan are here. And shall we move to the next stage of this talk?
Jonathan, I don't think you have your video on, your audio on. Are you muted? Yes, shall we get some of the questions in? I'm going to maybe ask one from Vinova. Vinova says, pardon me while I project my inner Black Mirror thoughts. It's interesting that the holy grail mentioned by Doron at the beginning is not an embodied neural implant. Why not an implant connected to everything around us?
Christoph, do you want to address this one?
Go ahead.
Well, you know, I think my sense is that BCI, medical BCI is going invasive. And look, Elon Musk is, you know, is an interesting character, but I don't think we should disrespect him for being an interesting character. And he's going invasive. So definitely, you know, you can have your implant sign up for the next human study by Neuralace. And seriously, when Mark Zuckerberg was asked, I think what he said is, look, as Facebook, you don't want to imagine the congressional hearing when I say that Facebook is doing invasive, you know, not only Facebook is following everything, we're just, you know, we're following thoughts. So I think Mark Zuckerberg would have gone invasive if he wouldn't been afraid of the consequences. Yeah, I don't see a big problem because I think we already have the problems. You know, the problems we have are not going to disappear or become greater because of implants. I think what we're probably going to see is that these things will take time. They will start with medical cases, which you can't argue with, helping people, helping locked-in patients, helping paralyzed patients. And after many years, this will be good enough, and maybe, you know, some generation will do it for, you know, cosmetic reasons or whatever.
It's just depending on the application, what you need for stroke rehabilitation. For example, you don't need a neural implant because the resolution on the surface is just good enough. Or for a locked-in patient to communicate with the speller, you don't need an implant because the EEG is, again, good enough. The other applications like deep brain stimulation and Parkinson's disease, where you have to implant something to stimulate the thalamus, of course. So it's just depending on the application, what you need.
Jonathan, do you want to share some of the questions?
Yes, definitely. So we had a few comments regarding the fMRI part. One from Katsia, that you know, from the Amedi lab, and also another question, and another one from Mohassin Rashid, who was asking, both of them were having some doubts regarding the fMRI and wanted to know in a bit if you can elaborate a bit more on the method used to classify the signals and how it operates in general, the motor imagery, fMRI.
Right. So I didn't have too much time to go into it, but basically you get the DICOM image from the brain pre-processed very fast with several milliseconds, like a 50 millisecond delay. And the first step is to reduce it from, I think it was something like 30,000, you know, or actually more. First of all, you using a simple threshold, you find the voxels that are in the brain and not outside the brain or eyes or stuff like that. We filtered the area of the eyes because we found out there's a lot of information where you're looking at it. We didn't want to cheat. So we're left with pure brain. That's relatively easy. And then you're left with something like 20,000 voxels, depends on the person. And the fastest thing and the best thing was to do information gain. So again, we need something like 40 repetitions. But after 40 repetitions, the SVM and tied to the information gain finds, voxels that are, most of them are really, really informative, and they're in the places that you would expect them in a classical study, distinguishing, say, left-right imagery. There's, of course, difference between motor imagery and motor execution, which is very, very important and often misunderstood. So, of course, fMRI allows you to look at all these things. So I'm not sure, again, what the questions are about, but of course, you can find many details in several papers written by, with the first author is Ori Cohen.
Great, thank you. Another interesting question that came from YouTube by Thomas Wutkowski, which is asking regarding something we used to discuss about the connection between VR and electrophysiology, specifically EMG and EOG, which is basically, it's a natural method that we can use for maybe, BMI.
Yeah, I want to address that because it relates to this neurochauvinism message that I was going to make. And so basically, I understand. So, in academia, it's very important for some of my colleagues who are, of course, really good researchers. And it's very important to distinguish and to say whether this is a pure BCI versus, and it's very important for them to insist that you're only using pure brain data in the interface. And I understand where that's coming from because you see too many misunderstandings, especially in industry. And you see a lot of videos on YouTube where people are controlling all kinds of things, but they're using actually muscle artifacts, right? To move things or to classify emotions. It's very easy to put EEG electrodes and to detect muscle activity and have an emotional classification. So I understand why in academia we try to be strict. But if you want to help people, if you want to have products and applications, then, it's kind of ridiculous to separate. Again, it's this kind of disembodiment trend, maybe a consequence of the information revolution. Like say, the brain is here, body is here, let's throw away the body. No, of course, you should use a mixture of channels. And whenever the easier channels do not work, yes, the EEG may help. I'm sure that you can build better solutions with a mixture of signals. We had 2 ALS patients, technically savvy, and they gave up using the BCI for communication. Again, we can discuss in depth with Christoph, but even at the last days when they were almost completely locked in, they usually had one residual muscle, which they could control and communicate using eye tracking, much faster than P300 BCI. They even tried Intendix or one of gTec products with Nadav's help in Israel. Now, I'm not saying BCI can't help anyone, but we see that pure BCI, I don't know, maybe Christoph, do you actually see, because maybe I'm wrong here and I would love to be corrected, do you actually see patients using P300 spellers, for example, other than experiments?
Of course, so we have a couple of clients, or actually many clients, using this speller for communication, and it's a very useful extension of eye trackers. And we always advise to start as soon as possible so that you don't lose the ability in communication. Some years ago, it was a big mistake that they got a brain-computer interface when it was already too late.
Mm-hmm.
For that reason, you have to start as soon as possible. That's also the reason why we developed the unicorn brain interface, which is just much cheaper than Intendix before. And for that reason, it's also affordable for locked-in patients and their families. And it's also much cheaper than an eye tracker. So an eye tracker for these patients is normally more than 10K, and the unicorn is 1K. So this is completely affordable for these patients and makes completely sense as a cognitive training environment beside the communication ability.
Yeah, I remember the issue with the timing definitely when we were trying these things, but my sense was that I would say the speed of communication, the satisfaction of the subjects, don't you think, Christoph, that integrating a multimodal interface would speed up communication?
You know, these patients are completely locked in and they are desperate to find a solution. And even if they're still good, you know, they want to have different options. If they become completely locked in to have different options available, they just sleep better if they know they have an iTrack and also a BCI system available if they become completely locked in. And for that reason, it's just very good to give them different options and possibilities for the futures when they are completely locked in.
Right.
Great, thank you. We have another question that from Daniel Salamanca, from the panelists here, from the audience on Zoom, who's asking, what are the possibilities of using BCI in a low budget way? I'd like to answer this shortly and also give Doron the option as well. And also, as Christoph just mentioned, gTec has a low budget device, right? And we're also familiar with the OpenBCI platform from the US, which provides experimental BCI operation using an Arduino supported platform and 3D printed headgear for the EEG, which is very useful and interesting to use. And I really believe that when the technology will be available for most use cases and not only research and so on, we will have many more applications regarding that. Go on.
And what were you trying to build with your students? Jonathan is the world champion in taking even non-technical social science students and getting them to build VR projects, BCI projects. I don't know, let's think what we had in the last few years. Anyway. Well, I gave these examples with the artists and
yeah, yes, definitely. So if somebody is interested in doing some BCI, you should definitely try and see if you can come across some low-cost devices from the Emotive, the Muse, maybe the OpenBCI platform. There, yeah, so there are many options. Another question from Muhsin Rashid, who asked that how can we understand brain is conscious or unconscious when we use BCI?
Mm-hmm. Yeah. So yeah, I didn't have time to go deeply into this, but of course it's a very good question. So consciousness, of course, is a very thorny issue. So, you know, depending on the context, you need to define it very carefully. And indeed, of course, in the paper, we don't call it consciousness to avoid all these misunderstandings. But I do believe that, I don't know if Christoph wants to tell about this because, you know, but I heard a rumor, okay, you know, as they say, someone said, maybe it's fake news, but imagine you could have a BCI control in your dreams, okay? So maybe it's fake news, but I heard Christoph is able to do this, or at least try to do this, and you can deny Christoph. But again, so that would be clearly a different conscious state. I wouldn't call it unconscious, but a different conscious state. So that's one example. If you can actually control BCI in your sleep. Another example would be, for me, the interesting thing, for example, in Jonathan's study, is that, or in a study by Michal Ramot, is that we made sure 100% that the people were not aware that they are controlling something, okay? So whether you call it conscious, unconscious, volitional, non-volitional, aware, unaware, yeah, that's what we're interested in.
So we are using auditory and vibrotactile BCI paradigms to find out in coma patients or patients with disorders of consciousness, if they have awareness and if they can follow conversations. So and this is simply done by putting EEG electrodes on, and then we run different experimental paradigms like low and high tones, di-di-da, di-di-da, and we instruct the coma patient, please count only the high tones. And if we find a nice brain response, then we have a very nice test that the patient was understanding it. In the next phase, you can also go to communication. So you can ask him questions like, do you like Doron? And did you study at IDC? And with the brain-computer interface, the coma patient can answer. And if most of the questions are correctly answered, then you get a very objective proof that he's understanding you. So
this is where I want,
very useful.
Yeah. Sorry, this is where I want to ask you, Christoph, ask you the same question that I asked Adrian Owen, of course, who did one of these first studies. How do you know that the patient is conscious?
Otherwise, he wouldn't be able to answer the questions. So we go from.
But you know that you can answer questions in your sleep, for example. Some people are able to.
We are testing command following and answering questions correctly. So if you answer 10 questions and you get 8, 9, or 10 correct answers, then you can assume that he is conscious.
Well, I think we would agree that it's a challenging question, but you know, at least in the original Adrian Owen. So for those of you who don't know Adrian Owen, check him up. And I asked him, like, in the original studies, it was very dramatic to find out that a lot of these coma patients were actually so-called conscious. And I asked him, how do you know they're conscious? And he said, well, I asked them. One of the questions I asked is, are you conscious? And they said, yes. But again, this is all I agree with the question that was asked because, you know, we do know that consciousness is a very elusive term and you can do all kinds of things during sleep or during alternate consciousness states. And yeah, but from a practical point of view, of course, you are assuming that they are conscious. Anyway.
Okay, shall I bring, do you have more questions?
We have some questions on the YouTube, but they're very technical regarding the devices and so on. There's one question regarding plasticity, which is interesting to ask because we know that it takes time to practice using BCI. And Doc Block is asking, have we run studies for enough time to see that the brain adapts to our system, which no longer recognize signals? I think that it differs between the fMRI and EEG system, but Christoph and Doron, I would love to hear your thoughts about this.
Can you repeat the question?
The question regards the plasticity effect that results in training using the systems. Brain plasticity.
I'm sorry, I'm not very good at multitasking. Christoph, do you want to take that?
So we use the brain-computer interface RecoverX, for example, for stroke rehabilitation. So we place EEG electrodes over the sensory-motor cortex because they have, you know, paralyzed limbs, hands or foot movements are paralyzed. And then we see with the brain-computer interface training that brain plasticity is happening very nicely. So normally we train these stroke patients in 25 therapy sessions. Each one lasts 45 minutes. So in total they have to train for 15 hours and afterwards we can just see very nicely that the sensory motor cortex is getting active again, even for the handicapped hand or handicapped leg. And this shows very nice brain plasticity with the EEG system. There are also studies from Vivek in Madison, Wisconsin in the USA, and he looked at fMRI pictures during the stroke rehabilitation training with BCIs. You can also see these brain plasticity effects in the fMRI images very nicely.
So yeah, I think now I understand the question. I do want to, yeah, this is one of the things, one of the reasons I think fMRI should be more friendly, part of the tools of the BCI community. And I suggest looking at a paper from Rafi's group. I think it was Tal Harmelech again, first author, which is called the day after effect. So basically finding after a neurofeedback session, a day after traces in resting state fMRI activity. There are some and that was several years ago. I'm sure there's more coming out. So there are ways to measure this kind of plasticity. and to see the brain reorganizing.
Great. And one last question from Robert Beraman, who is curious to hear your thoughts on what do you think will be the most promising technological advances for the near future regarding BCI?
Okay, here's where we should argue, but we won't. Again, I have the utmost respect for Christoph and his work in BCI, but I am a little bit impatient. So I would like to see new signals. Again, I would be very happy to be proven wrong, and to show. And if Christoph and other very excellent people in the field who are moving very, very slowly, step by step, squeezing what you can get from EEG and really make a difference in people's lives, and it is happening in Christoph's products. But I don't know. I guess I'm impatient. And I think I'm really hoping that some biophysicists, this is again not me, my background is more mathematical, algorithmical, come up with breakthroughs in channel, in brain information. Yeah.
It's actually very simple. So what you need is closed loop experiments. So you have to provide brain stimulation or full body stimulation, like functional electrical stimulation, to close the loop. And besides measuring the EEG and extracting your brain waves, you have to feed it back. And we have just seen it with recoveries, with the stroke rehabilitation. When we put in the functional electrical stimulation, then we get this pairing of cognitive processes with functional improvements and motor movements. And that's just a simple reason why we have the closed loop brain body
and
stimulation experiment.
Of course, that's the reason for using BCI with VR. That's why we started all these things in Presentia. So definitely on that, of course, we agree about closed loop, sensory motor, closed loop feedback, definitely multisensory, definitely.
On that note, I'm going to bring back Mel, who will give a wrap up.
First of all, it's Mel's fault. I wouldn't have, well, I don't think I would have gone into this. Well, anyway, and Mel is the one who introduced me to this field and to good friends like Christoph Guger. So Mel, your fault, please.
Yeah, I'd like to say that this journey started off in 2002 when we started this Presentia project, and this involved Doron, Christoph Guger, Perchula, and many others, or several others, and then we carried on in another project. And it's fascinating to hear how far it's come and also how far it needs to go. So thanks to Doron, Jonathan, and Christoph for presenting this work today. Thanks very much.
Thank you. Thanks a lot to Sylvia.
And to Sylvia, yes, for always being the producer behind the scenes. And I only want to finish by saying the next meeting, the next seminar will be by Mar Gonzalez Franco on the 4th of June. That's this Thursday at 6 o'clock CEST. That's Brussels time, or Paris or Berlin. So I hope you'll be joining us again on Thursday at 6 p.m. So thanks very much.
Thank you all.
Okay.
Bye.
Thank you. I'm going to stop the